In this lesson, we're going to be translating graphs of absolute value functions, stretch, shrink, and reflect graphs of absolute value functions, and then combine transformations of graphs of absolute value functions. An absolute value function is a function that contains an absolute value expression. The parent absolute value function is f of x equals the absolute value of x. The graph of f of x equals the absolute value of x is v-shaped and symmetric about the y-axis. The vertex is the point where the graph changes direction. The vertex of the graph f of x equals the absolute value of x is 0, 0, or the origin. The domain of f of x equals the absolute value of x is all real numbers. The range is y is greater than or equal to 0. A family of functions is a group of functions with similar characteristics. The most basic function in a family of functions is the parent functions. We will be looking at absolute value functions today, where the parent function is f of x equals the absolute value of x. All other absolute value functions are transformations of the graph of the parent function. A transformation changes the size, shape, position, or orientation of a graph. So I'm just going to show you how we got this graph right here. Okay. So the vertex is the lowest point, or the lowest y value, of the function f of x equals the absolute value of x. And the reason is because the lowest number that can pop out of an absolute value expression is 0. You can't have a negative number pop out of that. So I know 0 is my lowest number. So if I make a table, I have 0 in the middle. The absolute value of 0 is 0. If I take the absolute value of 1, that's 1. The absolute value of 2, that's 2. If I take the absolute value of negative 1, that is negative 1. The absolute value of negative 2, that's negative 2. So if I plot all these ordered pairs, and I can keep going with this pattern because it's not going to change. Then I'll draw my rays. That is how we get the absolute value parent function. A translation is a transformation that shifts a graph horizontally or vertically, but does not change the size, shape, or orientation of the graph. In function notation, a translation is represented by addition or subtraction. Remember, subtraction is just adding the opposite or adding the negative. Vertical translations occur outside of the function, and horizontal translations occur inside of the function. So before we get to doing this example, I'm just going to show you a quick example of translations on Desmos. So I'm on desmos.com right now, the graphing calculator, and this is our parent function, y equals the absolute value of x. Okay. Now I'm going to turn on this function. And what this is a slider, so k right now is equal to 0. So if I turn this on, it's going to be the exact same function. But if I increase this k value, so now I've set k equal to 3, you can see what happens. I've slid this graph up. It's the exact same graph, except for all the points, all the y values are just 3 units up or 3 units more. Now, if my k value is negative, for instance, negative 3, watch what happens. I'm sliding this down. So a translation, a vertical translation, means that I'm either moving the graph up or down. And notice when k is negative, I'm below my original function. And then when k is positive, I'm above my regular function. Now that's vertical translations, but let's look at horizontal translations. So I'm going to turn this off. Now I'm going to write y equals the absolute value of x minus h, and I'll add a new slider. So right here, I have the exact same thing because h is 0. Okay, so it's the same as my parent function. But watch what happens when I increase h. Okay, and notice this is minus. So right here, I have h equals 2. But that inside means x minus 2 means I go 2 to the right. And then if I make this negative, well, this is x minus a negative. Well, that goes to the left. So the inside is actually backwards. It's reversed. Okay, so anything that happens inside of the function is a little wonky, and that is the case for all horizontal translations. So what we know is that if it's really x minus 2, because that's what this is, that means I go 2 to the right, which is a little counterintuitive. But then if I do x plus 2, that's actually 2 to the left. Anyway, now we're going to graph each of these functions and compare each graph to the parent function, f of x equals the absolute value of x, and then describe the domain and range. Well, if I look at this first function, I can see that this is the original parent function just plus 3, and that is a vertical translation. Remember, vertical translations happen outside of the function. Okay? Well, another way to think of this is to find my vertex and then just graph. I could make a table if I wanted to, but you need your vertex as well. But because my x value is not changed, the x value of my vertex is still going to be 0, because the lowest value that's going to pop out of this absolute value function is still going to be 0. So I know that the x component is going to be 0, but then when I plug this in, I don't get 0 anymore. When I plug 0 in here, I actually get 0 plus 3, which gives me 3. So my new vertex is going to be 0, 3. And then from here, I could make my table. I could say, okay, if I plug in 1, the absolute value of 1 is 1, and then I get 1 plus 3, which is 4, and go here, and then do the same thing for 2, I get 5. But I could just say, okay, well, I know this is going to be a V-shaped graph, and I want to see, is my slope changing, or is the number that's being multiplied, my x, or my absolute value function, is that changing? And it's not. Well, that just means I'm going to have the exact same slope. You could also realize the coefficient here is 1, which means I'm going to get a slope of positive 1 going this way, and then negative 1 going this way. So you can just do that. So I have this going here, and then up 1, left 1 going here, and that's my pattern. I'm going to draw my rays. And now I need to compare this graph to my parent function. Well, the only transformation that's happened here is a vertical translation, 3 units up. So translate 3 units up. That's all I have to do to get from my parent function to my new function. And then describe the domain and range. Well, the domain is going to be all real numbers. So it's all real numbers. And then my range, well, let's look at my lowest y value. My lowest output value is 3. I can't have any value that's lower than 3 for my new function. So my range is going to be y is greater than or equal to 3. And now we're done with part A. For part B, let's take a look at this. If I do this the exact same way, I see that, okay, well, first of all, I have minus 2 on the inside of the function. And remember what I said, the inside works a little bit backwards, but you don't even really need to know that. What I do know is now I have something going on inside the absolute value, so that's going to change what my lowest value is going to be. 0 is no longer going to be the lowest x value that I plug in to pump out a number here. I actually need to set this entire thing equal to 0 to figure out what my x value, my vertex, is going to be. So if I do x minus 2 equals 0, add 2 on both sides, this is going to be the x value of my vertex, x equals 2. I'll write a little bit better 2 there. So now if I plug that in, now I get 0. So my vertex is going to actually be the point 2, 0. So that's my point here. And if you're wondering why, I plug 2 in here. 2 minus 2 is 0. Absolute value of 0 is 0. So when x is equal to 2, my output is equal to 0. So this is my vertex. And that is my only change. Once again, there's nothing being multiplied by x that's going to change the slope. And there's no negative sign, which you'll see in a moment is going to be reflecting our graph. So this is going to be the exact same slope. So from here, I go up 1, right 1, up 1, right 1, because my coefficient is 1. And then in the opposite direction, to keep that V shape, I have to go up 1, left 1, up 1, left 1. And once again, you always could make a table of values if you're not sure, but I typically find this way much easier. Now we need to compare each graph to the graph of f of x equals the absolute value of x, and then describe the domain and range. Well, notice my original graph is right here, and all I've done is moved this graph 2 units to the right. And once again, when I'm moving something or sliding it, that word is translate. So I'm going to translate 2 units to the right. And you don't even need to write to the right. You can just write translate 2 units right. And that's the only transformation. So now let's look at our domain and range. Once again, there's no number I cannot plug in. There's no real number that I cannot plug in for x. So my domain is all real numbers. And my range, well, let's look at my lowest y value. Okay, I don't have any negative y values, but 0 is a y value, and then I have all the positives. Remember, these arrows mean it goes on forever. So that means that my range is going to be y is greater than or equal to 0. And now we're done with this one. All right, so now we're going to talk about reflections and stretches and shrinks. So a reflection is a transformation that flips a graph over a line. This line is referred to as the line of reflection. So I'm going to go back to Desmos right now. So I have my parent function, y equals the absolute value of x. And now I'm going to type in y equals negative absolute value of x. And look what happens. Okay? So this right here is a mirror image, and it's on the outside of my function. Okay? All my vertical changes are going to happen outside of my function. Okay? In this case, my function, my parent function, is the absolute value of x. Okay? So since this negative is on the outside, this means it's a vertical change. So I've gone from the top, okay? So I'm in the positive world, and then now I'm at the bottom, which is the negative world. Okay? So this is technically a vertical change, but because my mirror is the x-axis, this is a reflection in the x-axis. Okay? Now, if I say, okay, now I want a negative on the inside of the function. Remember, the changes on the inside of the function are horizontal. So if I put the negative here, nothing happens. I get the exact same thing. Well, that should be kind of obvious because there can be no negative that pops out of an absolute value function. Well, what if I change my original function to x plus 2 and then make this one negative x plus 2? Okay? So now all I've done is I've changed the x, the sign of the x, I should say. So now this x instead of positive is negative. And look what happens here. Okay? So now this is the exact same thing, but instead of this x being without a negative sign, now I do have a negative sign on the x. And now it's symmetrical on the y-axis. So what that means is the y-axis is my line of reflection. And the easiest way to think about this is the y-axis is acting as my mirror. The red graph and the purple graph are a mirror image of each other. Okay? So remember, a negative on the outside, that's a vertical change. And if it's a vertical change, your x-axis is your mirror. And a negative on the inside, that is a horizontal change. And that means that my y-axis is my mirror. So that's a reflection in the y-axis. Now we're going to talk about stretches and shrinks. You can transform a function by multiplying all the x coordinates, or inputs, by the same factor a. When a is greater than 1, the transformation is a horizontal shrink because the graph shrinks towards the y-axis. When 0 is less than a is less than 1, the transformation is a horizontal stretch because the graph stretches away from the y-axis. In each case, the y-intercept stays the same. You can also transform a function by multiplying all the y-coordinates, or outputs, by the same factor a. When a is greater than 1, the transformation is a vertical stretch because the graph stretches away from the x-axis. When 0 is less than a is less than 1, the transformation is a vertical shrink because the graph shrinks towards the x-axis. In each case, the x-intercept stays the same. So let's go back to Desmos. So I have my parent function, y equals the absolute value of x. Okay? And now let's take a look at y equals the absolute value of, I'll do b times x, where b is just some number, and I'll add my slider. So right now, b is 1. And remember, this b is on the inside of the function. So we should be expecting a horizontal change. But also remember that my changes inside the function are typically reversed than what we expect. So because this is going to be a horizontal change, I want you guys to think of what's happening with the y-axis. Okay? So as I increase b, so let's say from b goes to 1 to b now is at, let's say, 3. Notice that I have squished this graph horizontally. So this graph right here is moving in, and then same thing over here. So that's moving in here. So this is actually a horizontal shrink because I'm squishing it towards the y-axis. If you look at it from a horizontal lens, it's getting compressed. Okay? So this is actually a horizontal shrink. My scale factor is actually not 3, it's 1/3, because when we take a horizontal shrink, we're taking the reciprocal of the number that's being multiplied by x. Now, when I decrease this from the y-axis, I'm actually stretching it out. Okay, so now I'm back to 1, and let's say I have this number in between 1 and 0. So let's go to 0.5. So if you look at this from a horizontal lens, from this point to this point, I'm actually pulling it away from the y-axis. Okay, so this is a horizontal stretch. And my scale factor is actually not going to be 0.5. It's going to be the reciprocal of that, which is 2. So this is a horizontal stretch with a scale factor of 2 because my y value is staying the same, and my x value is getting doubled. Now I'm going to change this b on the inside to an a on the outside. Okay, so now this is outside of the function, and that means that we should be expecting a vertical change. Okay, now vertical changes are much more straightforward. They're not reversed like horizontal changes. So if I take this 1 right here, and we're looking at it from a vertical lens, so up and down. Let's see what our new function does. Okay, you might say, okay, this looks like the exact same thing. And you might be right, because you can look at horizontal stretches and describe them the exact same way using vertical stretches, and we'll get to that once we get to vertex form. But just look at what's happening here. Okay, so this is on the outside. If I take this point right here, -2, 2, okay, well, all I've done, since my scale factor is going to be 2 here, all I've done is move from this -2, 2 to -2, 4. So every point right here with our original graph, the new output is double that. Okay, so that is a horizontal stretch because I'm stretching it away from, this time, the x-axis. Once again, I'm pulling it away from the x-axis. That's a vertical change. That's why my a is on the outside. And then now I'll get this number in between 0 and 1. So let's say 0.5. There we go. So now I'm pushing this towards the x-axis. Okay, I'm compressing my graph towards the y-axis. I'm squishing it, so that's why this is a vertical shrink. So this would be a vertical shrink with a scale factor of 0.5. So that was a lot, but now we're going to graph these two functions and then compare each graph to the graph of f of x equals the absolute value of x, and then describe the domain and range. So right here I have q of x. Okay, now whenever you're graphing an absolute value function, I still think it's the best thing you can do first is to find the vertex. Okay, well, there's nothing that I'm adding to my x value inside or outside. Well, that's good for me. That means that my my vertex is going to be the point 0, 0. So if I have 0, 0, that's my first point. And now I have this 2 on the outside of my function. Well, let's see what that 2 does. This 2 is going to be a vertical stretch of my graph. Okay? Another way to say this is my slope initially was going to be 1, just like this graph that's already drawn here. But now my slope is going to be 2. So instead of going up 1, right 1, up 1, right 1, I'm going to go up 2, right 1, up 2, right 1. And then over here, I'm going to go up 2, left 1, because going this way, it's going to be -2. So this is going to be my new graph here. And once again, you could always make a table from your vertex to see if this is the case. Like, for instance, if I said x is -2, the absolute value of -2 is 2 times 2. Well, that gets me my 4 here. Okay, so all I have to do is say, okay, I have this graph right here. The only thing that's happening is this vertical stretch. And now my slope has just changed from, instead of -1 and +1, now it's -2 and +2. And now I'm going to draw my rays. Then we're going to compare each graph to our parent function, which we just said. This is vertical stretch, a scale factor of 2. Okay, and remember, it's a vertical change because it's happening outside of the function. Now, I need to describe the domain and range. Domain, all real numbers, because I can plug in any number here. And my range is going to be, well, my lowest y value is still 0, so it's going to be y is greater than or equal to 0. Now we're done with this one. Okay, for part B, well, I have something that's going on outside of my function again, which is fine. But let's take a look at this. Okay, I have a negative sign here. Okay, up until now, all of my absolute value graphs have been V-shape. But when I looked at what this negative on the outside does, remember, it's a vertical change. So instead of all these numbers being in the positive part of my graph, they're all going to be in the negative part of my graph, and that's in terms of y value. Okay, so I'm going to be flipping this over the x-axis. Okay, so this negative means I'm going to have a reflection in the x-axis. And basically, you can always tell if your graph's going to be a V or an upside down V if you have a negative outside of the absolute value. Okay, and then this 1/2, well, here I was multiplying by a number that's larger than 1, and then here I'm multiplying by a number that is in between 0 and 1. So this 1/2 is actually going to be a vertical shrink by a scale factor of 1/2. Remember, it's vertical because it's on the outside. It's a shrink because it's in between 0 and 1. But remember, the first thing that I always recommend doing is finding the vertex. Well, there's nothing being added here as well. So my vertex is still going to be 0, 0. If I plug in 0 for x, I'm going to get 0 for y, or my p of x value. And the reason is because 0 is still the lowest number that's going to pop out of this absolute value function. So my vertex is going to be 0, or the origin right there. But now I know the negative means I have an upside down V shape. Remember, this is for the negative on the outside. So instead of going up one, right one, I would go down one, right one, or down one, left one. But my new slope is not going to be 1 and negative 1 anymore. It's going to be 1/2. Okay, so instead of going down 1, right 1, I'm going to go down 1, right 2. Down 1, right 2. Then here I'm going to go down 1, left 2, down 1, left 2. Okay, I'm going to draw my rays. And then I need to compare each graph to the graph of f of x. So remember, this is going to be a vertical shrink and a reflection in the x-axis. Okay, that's what the 1/2 is, the vertical shrink. The minus sign is the reflection in the x-axis. Now, the order of these two things do not matter. I'd recommend doing your reflections in the x-axis and your vertical stretches or shrinks first, and then your translations afterwards. If you do it in that order, and you'll see why once we go over vertex form in just a moment, but if you do it in that order, you'll be correct every time. Another way you could do it is do your horizontal translations first, then your stretches and shrinks, then your reflections, and then end with your vertical translations. But I think that the way that I prefer to do it is a bit more streamlined. Anyway, so I'm going to write down reflection in x-axis. Because remember, even though it's a vertical change, the x-axis is my mirror, so that's my line of reflection. And then vertical shrink, the scale factor of 1/2. Okay, and then the domain and range. So the domain is going to be all real numbers. And the range, in this case, is not going to be y is greater than or equal to 0. 0 here is my largest value. So it's actually going to be y is less than or equal to 0, because I don't have any positive numbers. I just have 0 and all the negatives. So y is less than or equal to 0. And now we're done with this one. Now we're going to talk about vertex form of an absolute value function. An absolute value function written in the form g of x equals a times the absolute value of the quantity x minus h, all plus k, where a is not equal to 0, is in vertex form. The vertex of the graph of g is h, k. Any absolute value function can be written in vertex form, and its graph is symmetric about the line x equals h. Well, let's figure out why that's the case. Remember, earlier in the video, we wanted to find the vertex when we were graphing our functions. Well, the vertex is when this absolute value expression is equal to 0. So if I do x minus h is equal to 0, all I got to do is add h on both sides. So my x value is going to be h. Okay, so if I plug in h here, that makes it 0. That is the lowest value that's going to pop out of this if a is positive, or the largest value if a is negative. And then if this whole expression is 0, if I plug in h here, h minus h, absolute value of that is 0. So I get a times 0. And remember, there's a plus k here, plus k. So that's why I get h comma k. Okay? Now, even if we see a function that is not in vertex form, any absolute value function can be written in vertex form. So we can always think of it as vertex form. So for instance, let's say that I had h of x equals the absolute value of bx minus h plus k. Well, what I'd recommend doing is still finding the vertex. And what we do is we set this whole thing equal to 0. So bx minus h equals 0 plus h. So I get bx equals h, and then divide by b. And that is a way that to find our x component. And the y component is just going to be whatever is being added to this absolute value expression. So in this case, my vertex would be h over b, comma, k. So even if it's not in vertex form, you can still find the vertex by setting this inside of this absolute value expression equal to 0. And then when you plug that in, the whole thing will go away. And then you'll be left with your y value of your vertex. And then you use that to graph. So for this example, we're going to graph f of x equals the absolute value of x plus 3, all minus 3. And then g of x equals the absolute value of 2x plus 2 minus 3. And then we're going to compare the graph of g to the graph of f. Well, first I'm going to graph f. And remember, I want to find my vertex. So I'm going to set this whole thing equal to 0. So x plus 2 equals 0. Subtract 2. And you could probably do that in your head if you wanted to. But x equals negative 2. So I know negative 2 is the x value of my vertex. And then I see that I have negative 3. Remember, if I plug negative 3 into here, this whole thing's going to cancel. So I'm just going to get negative 3 here. So if I plug negative 2 into here, this entire absolute value expression is going to cancel. So I'm just going to be left with negative 3 as my y value of my vertex. So the vertex is negative 2, comma, negative 3. Okay? So that is right here. So negative 2, negative 3. And then I want to see, is there anything being multiplied by my x? Well, there's not anything being multiplied by x, either on the inside or the outside. So my coefficient is 1, which means for a v shape going to the right, my slope is 1 over 1, and then going to the left, it's 1 and then left 1, so it's negative 1 over here. So I can go up 1, right 1 for positive slope of 1, then up 1, left 1 for a negative slope of 1. Okay? And then I'm going to draw my rays. So now I want to graph g of x equals the absolute value of 2x plus 2. So do that in red. And remember, when I want to graph this, first thing I want to do is find the vertex. So I get 2x plus 2. I need to set this whole thing inside the absolute value equal to 0 to find the x value of my vertex. So 2x plus 2 equals 0, minus 2 on both sides. So I get 2x equals negative 2, then divide by 2 to get x equals negative 1. So the x value of my vertex is negative 1. Write vertex here. And then when I plug in negative 1, I know this whole thing's going to equal 0. So this whole entire absolute value thing goes away. So the only thing that's left is the corresponding y value, or g of x value, which is going to be negative 3. So the vertex value for my y value is negative 3. So I'm going to plot this point, negative 1, negative 3. That's right here. So now I need to figure out, okay, well, what is being multiplied by x? And in this case, it actually doesn't matter if it's on the inside or the outside. If there's two numbers, we're going to end up multiplying them together. So I have a 2 being multiplied by x. So that means that my slope now is no longer going to be 1 over 1 and 1 over negative 1. It's going to be 2 over 1 and 2 over negative 1. So if I go up 2, right 2, and by the way, we know it's not going to be an upside down v because there's no negative on the outside. So anyway, for a v shape with a slope of 2 and negative 2, I'm going to go up 2, right 2. Up 2, right 2. I'm saying up 2, right 2. I mean up 2, right 1. Sorry. And then going to the left, I'm going to go up to left 1, to left 1, and so on. Now I'll draw my rays here. And now it's asking me to compare the graph of g to the graph of f. Well, if I look at this, I see that I have a number inside of my absolute value expression, and that's the only difference. The rest of it's the same. The plus 2 is the same, the minus 3 is the same. So this 2, remember, if I'm multiplying a number inside, that's going to be a horizontal stretch or shrink, and because the 2 is actually above 1, remember, things on the inside are backwards for horizontal changes, so that's actually going to be a horizontal shrink. And the reason I know that's going to be the case is because if I look at my y-axis, all of my original graph I'm squishing by a factor of 1/2. Okay, so this is getting closer to the y-axis. Say, so this point right here for my x value of negative 6, my y value is 1, and then here the x value is going to be negative 3 for a y value of 1. Same thing here. You can look at any of the points. Okay, so this point would be cut in half, this point would be cut in half. So anyway, the transformation is going to be a horizontal shrink with a scale factor of 1/2. Remember, the number that's being multiplied on the inside, since it's reversed, I take the reciprocal of this number, which is 2. So I take the reciprocal of 2, that's 1/2, and that's how to get my scale factor for my horizontal shrink. Remember, it's a horizontal shrink because I'm compressing it towards the y-axis. It'd be a horizontal stretch if I was pulling it away from the y-axis, but this one is a horizontal shrink. For part B, we're going to graph f of x equals the absolute value of x plus 2, all minus 3, and then h of x equals the absolute value of negative 0.5 x plus 2, and then all minus 3. And then we're going to compare the graph of h to the graph of f. Well, this graph is the exact same one that I just graphed. So if I go back up here, it's this graph. We already did it. I'm not going to waste your time graphing it again. But I figured out that my vertex was negative 2, comma negative 3. And then my slope is going to be 1 and negative 1. I'll draw my rays really quickly. And now I want to graph h of x equals the absolute value of negative 0.5x, and then plus 2, and then all minus 3. So before I even do anything, I know that I have a number that is less than 1 and larger than 0, so 0.5 is being multiplied by x. And then I have this negative sign. So we'll see what that's going to do in just a moment. But once again, the best way, in my opinion, to graph these functions is still find the vertex by setting this whole entire thing equal to 0. So I have negative 0.5x plus 2 equals 0. And then I get minus 2 over here. Negative 0.5x equals negative 2. Then I'm going to divide by negative 0.5. That's the same thing as multiplying by 2. So if I divide negative 0.5, sorry about that. And then I just get x here. And remember, dividing by negative 0.5, well, the negatives are going to cancel. And then dividing by 1/2 is the same thing as multiplying by 2. So 2 times 2 is 4. So the vertex x value is 4. And then when I plug that in, this whole thing's going to end up 0. My y vertex is still going to be negative 3. So my vertex is going to be 4, comma, negative 3. Okay. Well, now what I'm going to do is plot this point. And I'll do this in red. So I'll just make sure that we know that that's the correct point. So 4, comma, negative 3. That is my vertex. Okay. And I'm kind of running out of space on my graph here, but that's okay. And then now what I want to do is figure out, okay, is this going to be v or upside down v? Well, let's see. Do I have a negative on the outside of the absolute value? I do not have a negative on the outside of the absolute value. So I'm still going to have a v-shaped graph. Okay? Even though I have a negative inside, that's not going to be flipping me from a regular v to an upside down v. You'll see in a moment what that's going to do. So now I just need to figure out what the slope is going to be. Well, the only coefficient is 0.5, and I have a negative. But remember, I'm going to have both a negative and a positive. So going this way, since I want a regular v, it's going to be 0.5. And then going this way, my slope's going to be negative 0.5. So I can only fit on this point on my graph, so it's going to be up 1/2, right 1. Then over here, I can go up 1/2, left 1, or up 1, left 2. Same thing. And I keep going with that pattern. Now I'm going to draw my rays. So then this is my graph for h of x, and now I need to compare this. Well, first let's look at the 0.5. Okay? Remember earlier, I looked at the 2. The 2x meant that I had a horizontal shrink with a scale factor of 1/2. Okay? But remember, since the inside of my function is reversed, what I can actually do is I know that this 0.5, I'm actually stretching it away from the y-axis. Okay? So, and this scale factor is going to be by a factor of 2. Okay? So for instance, this point right here on my original graph is 1 unit away from the y-axis. This one is 2 units away from the y-axis. And then we're going to talk about why it's on the other side in a moment. But first I'm going to write down horizontal stretch with a scale factor, that's what fs means, of 2. Okay? And remember, I take the reciprocal of this 0.5. Okay, because it's on the inside of the fraction, or inside of the function, I should say. And now I need to deal with this negative. Well, remember, a negative on the inside, that's going to be a reflection in the y-axis. Okay, anything on the inside is a horizontal change. Okay, so if I'm going from the left side to the right side, that means that I have my negative is acting as a reflection in the y-axis. So I need to put that as well. Reflection in y-axis. Okay, so we've done 2 examples, one with a horizontal stretch, one with a horizontal shrink. Okay, but this is how to compare 2 graphs and describe how to get from one of them to the other one. And now we're done with this one. So we're going to graph g of x, and then we're going to describe the transformations from the parent function f of x equals the absolute value of x. So anytime I'm graphing an absolute value function, the first thing I want to do is find the vertex. Then what I want to do is figure out whether or not it is going to be a V-shaped graph or upside down V-shaped graph. And then last, what I want to do is figure out the slope. and there's going to be a positive and negative slope. So I really just need the absolute value of that slope. And that number is just going to be the number that's being multiplied by either x or the absolute value symbol. So in this case, to find the vertex, to find my x component, it's whenever x, this expression, x minus 1, is equal to 0. So I'll set x minus 1 equal to 0. And you could do that in your head, but if you add 1 on both sides, you get x equals 1. So the x value of my vertex is 1. And then the y value of my vertex is always the number that's being added to the absolute value expression. So in this case, it's positive 3. If I saw a minus sign, it'd be minus 3 or negative 3. So my vertex is 1, 3. So I'll write that as an ordered pair. So once I find my vertex, I can plot that. So I'll plot 1, 3. And then the next thing I want to do is figure out if it's V-shaped or upside down V-shaped. Okay, well, the way I do that is very simple. I just see, is there a negative sign on the outside of my absolute value expression? And there is one here, so that means it's going to be an upside down V. So I know that it's going to be pointing down like this rather than opening up like this. Okay. Now the last thing, which I forgot to write down, is the slope. Okay, now the slope is going to be positive and negative because it's going to go in both directions. I know it's going to be upside down V, so I just need to figure out what that number is. Well, in this case, I have this 2 that's being multiplied by my absolute value expression. Okay, so that is going to be my slope. It's going to be plus or minus 2. On the rare chance that you have a number outside and inside here, you would just multiply the absolute values of those numbers. So if it was a 2 here and then a 2 here, I do 2 times 2 is 4. But more common, you'll just see one number either on the inside or the outside. So now I can easily graph this. So I know it's going to be going like a V-shaped, upside down. So here I want to go down to left one and down to right one. And I can keep going with this pattern until I can't fit any more points on the graph. Now I'll draw my rays from my vertex that goes through the points. The last step is to describe the transformations from the parent function. Well, so if we treat this like we're in vertex form, and this actually is in vertex form, it's really easy to describe the transformations. Okay, so the first thing I want to do, and I'll make some space here, maybe zoom out a bit. The first thing I want to do is describe the a value. And if you don't know what I'm talking about for vertex form is y equals a times the absolute value of x minus h plus k, where h and k, or this is the x value of the vertex, y value of the vertex. Okay. So first thing I want to do is start with my a number here. So my a not only has the reflection, but it also has any vertical stretch or shrink. Now, I'll start with the reflection first, but it doesn't matter which one you start out of those two. And basically, is there a reflection in the x-axis? And since this is an upside down V, yes, there is. So my first transformation is going to be reflection in the x-axis, okay? The next thing I want to do is figure out if there's a vertical stretch or a vertical shrink, or nothing. Okay, so in this case, the slope is not 1 or negative 1, so that means that there is a vertical stretch or shrink. And in this case, it's going to be a vertical stretch because my slope is larger than 1. If my slope was a fraction in between 0 and 1, like 1/2, then it would be a vertical shrink. So this 2 right here means I have a vertical stretch with a scale factor of 2. And then last, the reason why I like doing it this way, last, the translation is just going to be the vertex. So my vertex is 1, 3. That just means I translate 1 unit right and 3 units up. So we've successfully graphed g of x and then described the transformations from the parent function f of x equals the absolute value of x. So now we're done with this one. For this one, we're going to graph h of x and then describe the transformations from the parent function f of x equals the absolute value of x. So it's a very similar type of question that we had in the last example. But notice, now I have a coefficient that's on the inside of my absolute value rather than the outside. Okay? So there's multiple ways to do this, but I'm going to show you the best way that I think and the easiest way that I think there is to do this. Okay? So first thing we're going to do is find our 3 things. Vertex, V or upside down V, and then the slope. So once again, to find the vertex, you just set this entire expression inside the absolute value equal to 0. So I'll do that. 1/2 x plus 1 equals 0. Subtract 1 on both sides, so I get 1/2 x equals -1. Multiply both sides by the reciprocal of 1/2, which is 2. So I get x is equal to -2. The x component of my vertex will be -2, and the y component, if you remember, is always going to be the number that's being added to this absolute value expression. In this case, I have a negative number, -3, so that's my y component of the vertex. My vertex is the ordered pair -2, comma, -3. So I'm going to plot that point right now, -2, -3. Now, I want to figure out is if my graph is going to be a V shape or an upside down V. Well, there's no negative on the outside, and that's all I need to check for, so it's going to be a regular V. And then all I need to do is figure out the slope. Well, the slope is just going to be the number that's being multiplied by x. In this case, that's 1/2. So it's going to be positive 1/2 and negative 1/2. So I'll write that down here. And then from my point, I can just go, I know it's going to be V-shaped, so I can just go up 1, right 2, and continue doing that, and then up 1, left 2, and continue doing that. So that's up 1, right 2, and then up 1, left 2. Okay. So now I'm going to draw my rays from my vertex that goes through these points. All right. And then last, I just need to describe the transformations from the parent function. Well, you could do it the normal way, the way that the function looks like. And in that case, you'd basically do your horizontal translations first, then figure out if there is a reflection in the y-axis, which there's not here, then figure out your horizontal stretches or shrink, which there's a horizontal stretch of a scale factor of 2. Then figure out if there's a reflection in the x-axis, which there is not because there's no negative sign out here. Then figure out if there's any vertical stretch or vertical shrink, which there's not because there's no number being multiplied by this absolute value expression. And then you end with the translations that are vertical. Now, I think that is way too much. I think that's a bit overkill, and there's a faster way to do it. And the way to do it is to think of everything, once again, like it's in vertex form. Because you can rewrite any absolute value function, including this one, in vertex form, which once again is y equals a times the absolute value of x minus h plus k. Okay? So all I need to do is describe my transformations based on this, and that's still accurate. It's still a way to get from a parent function to the function that I just graphed. Okay? So first thing I'm going to start with, once again, is there a reflection in the x-axis or not? Since there's no negative out here, and since it's a regular V-shaped instead of upside down V, there's no reflection in the x-axis, so I don't need to write anything there. The next question I want to ask myself, because I'm still dealing with this a term, is my slope equal to anything but 1? And my slope is not equal to 1, it's equal to 1/2. So that means that there has been a vertical stretch or shrink. And since 1/2 is in between 0 and 1 and not greater than 1, it's going to be a vertical shrink. So I can think of this as a vertical shrink. And the benefit of thinking of everything as a vertical shrink is your scale factor is just the slope. If you remember, the horizontal scale factor is the reciprocal of the slope. But in this case, it's just a vertical shrink with a scale factor of 1/2, which is my plus or minus my slope. Okay, so I've done that, and now all I have to do is deal with my translations, which, remember, if you do it this way, your translation is always going to be the vertex. In this case, -2, comma -3, that's just left 2, down 3. So I'm going to write translate 2 units left and 3 units down. So I think this is the best way to not only graph absolute value functions, but describe their transformations from the parent function.